Good afternoon, everyone. I'm Hanan Al Hassan, and I'm going to be the moderator for this session today. First of all, I'd like to welcome you all to the 10th virtual technical session on subsurface risk monitoring for the management of a CCS site. And before we get started, I'd like to inform you that the session will be recorded and published on our social media accounts and YouTube. At the end, we'll have a Q&A session. So kindly, if you have any question, you can write it in the chat box or raise your hand for a question. And now it's my pleasure to introduce Mr. Francois Bouchet. He's a technical advisor, Asset Consultant Services, Schlumberger. Mr. Bouchet is a well-rounded subsurface geoscientist with extensive exposure to reservoir engineering and production, and experience from various regions on the world and different type of geological settings. He worked for over 33 years in studies, successfully as a geophysicist and geologist in an operating company, Shell, and as a senior geoscience and reservoir engineering consultant with IFP and SLP. He has carried out multiple projects, both in exploration and field development, as a petrotechnical professional. Mr. Bouchet is a technical advisor and SME for various subsurface domains, and is providing subsurface project peer review for SLP consultant services worldwide. He has been actively involved in more than 10 different CCS projects over the past 4 years, including projects in Egypt, Saudi Arabia, and the UAE, as well as Malaysia, US, Colombia, Denmark, UK, and Brazil. Mr. Francois, the floor is yours. You can present.
So thank you very much for the introduction, and thank you for having me for this presentation. I selected the topic of subsurface risk monitoring for the management of a CCS site to give an overview of what should be done to reduce risks, to have the best management possible of a CCS site. And what I'm going to try to emphasize in the next 45 minutes, which are all these different items, so there's quite a few to cover, is to give a broad picture of what is required in CCS site management to reduce risks. And I would also convey the message of how different it is to reduce risk for a CCS project versus reduce risk for an oil and gas business. So to do this, I will go through some basic element, which is a short introduction on the concept and drivers. We looked at risk and the risk definition. Then we looked specifically at two areas, the wells and the reservoir. So wells and reservoir are the two components of a subsurface we're going to focus on when we're going to look at risks. We're going to then look at historical cases. Why historical cases? Because we have lesson learned from the past 20, 25 years of injection of CO2 in the subsurface for storage. And these examples illustrate some of the risks and make them really understandable. Then we go through conclusions and we'll have some time for questions and answers at the end. So with the first part on the introduction, I want to highlight this is a very different business. It has like an oil and gas operator, customer, and an authority that is regulating it. But because we're not producing oil that we're selling, but we're collecting gas that we make disappear, at the end of a process, there is nothing to show. The gas is underground. It's nothing of value that we can sell like when we produce oil and gas. So the relationship between the different partners here is very different. And the way it works, basically the customer, which is an emitter of CO2, gives us some CO2 for us to dispose of. And we dispose of it safely by putting it underground forever. And we do it, and we report to the authority that we have put it in the ground, and the authority then gives us a credit, a carbon credit. Then we pass that carbon credit to the customer that then pays us for disposing of the CO2. Because we do it on a monthly basis and yearly basis for the authority, we have to report of the performance of the site extremely regularly, far more than what you would do for an oil and gas business. And because we interact with the customer, taking care of his CO2 and avoiding him penalties and fees, we commit to supporting it for a very long time without failing. Basically, we tell them, and we enter a very large and very long contract, and these large and long contracts are long-term commitments. This is a little bit closer to the gas business, where we enter a long-term commitment to produce. It's very different from oil, which is on the spot market. And these long-term commitments have penalties associated to it and obligations. Now let's look a little bit more at the CCS site, what these CCS sites are. Basically, we collect from an emitter, here a company producing electricity power plant. We collect the CO2, we maybe process it, then we compress it, and we inject it through our injection well into the reservoir underground. This is our reservoir in gray. And the reservoir is capped by seal. And the injection that we take here in our well then progressively fills up that reservoir. That's the concept of our CCS site. So we bring CO2 that is produced industrially or that's coming from the consumption of hydrocarbon, for example, and then we actually store it in a place which is away from the atmosphere and is going to be away from us for global warming. Now, what are the technical performance factors? First, there's a lot of factors we consider when we want to look for a good site. But one of the three performance factors, which are the technical performance factors, are grouped in three categories: capacity, which is how much we can actually store; injectivity is how easy is it that we can store, and this injectivity directly impacts the number of wells that we need to drill. If the injectivity is low, we'll need to drill a lot of wells, or we need to put a very high pressure. Both of them are more costly. Finally, the containment is a very important one. We want to put the CO2 underground in the reservoir, and we want the CO2 to stay there. Containment is therefore very, very important to guarantee that the CO2 is not coming back to surface. This actually is particularly of importance for the regulator. And in most of the cases, the carbon credit that we get from the injection can be cancelled or have to be refunded to some amount if there is a leakage. These amounts can be very significant if you have a very large leakage. Therefore, the containment is not only a regulation obligation, it is a survival which is very important for our project, both for our customers, that if their carbon credit are cancelled, then we will need to refund them, and for the public opinion that actually has a very important view on any leakage that could happen. Public opinion is not too concerned about capacity and injectivity. This is a technical issue, but containment has got many stakeholders, and therefore the demonstration of proper containment is critical. If you fail, you may lose your license altogether and have to stop injection, with the consequences of having a significant amount of investment to build up your site and not the possibility to inject and to recover your money and make it profitable. Now, the main concepts and features for CCS site are very different from oil and gas. First, CCS stands for carbon capture and sequestration. Sequestration means that we're going to keep this site, the CO2 in this site forever. We're not storing it for later utilizing it. We actually not wanting it to get it back. And that's the main part. These are very large amounts. Of course, we know that we store CO2 to have utilization in different cases, but the amount of utilization is very small compared to the amount that we need to sequestrate to meet the objectives of reduction of CO2 in the atmosphere. Secondly, these are very long-term projects. We're going to inject for 30 years, 25 years, 30 years. We're going to be liable for the site for another 10, 20, 30, some cases even 50 years. And this liability is actually with the regulator. So even after we finish the injection, we still need to monitor the site to make sure that there is no leakage. This is a very large CapEx and OpEx, and the CapEx is all up front. You're going to set the pipelines, the compressors, and all the subsurface wells up front. So there's a very upfront part on your project in terms of a very large CapEx, which you recover through the fees you charge for injecting. Now in the subsurface, it's very important to get to the right place. Why? Because although it's a very small amount of a CapEx, about 15% of the total CapEx, meaning 85% will go into the pipelines, the compressor, and all these elements. Although it's a small amount of the CapEx, it's most of the risk. And we'll see why it's most of the risk. The reason is simply we don't know the subsurface very well. Even if we think we do, we don't, and we cannot remediate it. If you have an incident on surface, you can change your compressor. It's costly, but you can change it. But you have an incident in the subsurface, how will you recover if you start to have a leakage? So these are the main points that you have. I'd just like to highlight that very recently in COP29, to COP29 in few days ago, the carbon market has finally been approved. So after 9 years of discussion, where it was initially designed and defined in 2015 in Paris, it has been signed in 2024 in Baku. So that's just to keep it up. It seems that the community wants to continue with the carbon market, and that carbon market will open up for commercial use of sequestration. Now let's look at the mechanism for sequestration. There are two types of mechanism that we consider: structural trapping, which is something we are very familiar with. We have a structure, and within that structure, which is closed, with a spill point and with a top seal, then we have a space of permeable and porous reservoir, and we can fill with CO2. Now this applies to depleted gas field very well, because, and we'll see why, because a lot of interesting aspect of depleted gas field is easy storage. But it does not apply necessarily to all the storage site. Actually, if we compare worldwide, the storage in aquifer offer about 1,000 times more storage than the depleted gas field or the existing structures. How does that work? What is most important is that there is actually no closure in a saline aquifer. The saline aquifer is open. We have a top seal that prevents the CO2 from going back to surface. And we have injection in that reservoir that is providing the injection of the CO2 in the aquifer. Now, the strange thing is that because we have to remember that we would select a very large, very thick reservoir and very extensive reservoir. That's the first criteria. The amount of CO2 we store in this place is comparatively small to the overall volume of the reservoir. So as we inject our CO2, the CO2 will migrate in the reservoir and will occupy the pore space and will extend. And it will move through the reservoir and move out probably to an area which is higher in position. But because the amount of CO2 we inject is comparatively very small compared to the entire size of the reservoir, the bubble of CO2 will move slowly. It will fragmentate in little bubbles as the plume that we call this amount of CO2 is moving out or moving away from the well, it will leave behind residual saturation in gas, and this residual saturation in gas will be just droplet. So this amount of CO2 that we inject will progressively move out, but it will leave behind a trail of residual CO2 inside the reservoir, which means that as it moves, the plume of the CO2 progressively diminishes in volume, leaving only behind small amount until the time it is all reduced to residual gas saturation. Over time, this saturation will actually equilibrate with the water by dissolution, and the CO2, which is in these small bubbles, will continuously dissolve. And over a very long period of time, it takes sometimes probably around 1,000 years. In our simulation, we observe not even full dissolution after a couple of thousand of years. So it's actually a very, very long process, but at the geological time that we are considered, it's a very safe and very secure process. Of course, if the horizon is almost horizontal, so we do not inject this in areas with strong dip, we would inject this in areas where the dip is not very high, then this plume will move very, very slowly. So it will still remain around the injection point. And this is an important aspect because when we go to the injection for the license, you need to inject in the license space that you are given. And generally, there's a geographical limit that you cannot exceed. So I've already discussed those 2 points, and I wanted to here only highlight how they differ. So a depleted gas field has got a lot of elements that we know of because we've got a lot of wells drilled and we've got a long production history. So what do we know? Generally, we know the capacity because we know how much gas we produce, and therefore we know how much CO2 we can store in there. We have a very good idea of injectivity will be because we have production rates. So our production rates calibrate our permeability in the reservoir and the connectivity in the reservoir, and we know how the injectivity will respond to that. So capacity and injectivity, 2 critical technical criteria, we already know. And the containment, the risk is small. It's not negligible, but it's small. Why? Because we inject into a gas reservoir. So there was before a seal component to it. And therefore the seal is by essence proven. There are 2 points of attention. The seal might have been damaged during depletion because during depletion, if the depletion is very severe, there could be compaction, there could be fracturing of the seal, and there could be a weakening of that seal. And then secondly, the point is that the volume is actually not necessarily sufficient. When we look at injection, and this is the case for commercial project, you look at a minimum of 1 million ton per annum for 25 years. In the case of Kuwait, Saudi Arabia, and others, we are looking at much more ambitious targets. We're looking at 20 million ton per annum over the same period of time, or 40 million of ton per annum for the same period of time. Now, 1 million ton per annum for 25 years is half a TCF. So the reason why I point out 1 million ton per annum, because this corresponds to about 50 million cubic feet a day, which is one well. One well, one site, one well, 25 years, it's half a TCF. Therefore, if you want to consider a site, you should consider as a depleted gas field, you should consider depleted gas field which are in the TCF range, at least half a TCF. Now for aquifers, the problem is very different. Generally, we've got very, very little information. We don't know whether there's a seal, the top seal is working because it's never been proven. We don't know whether the injectivity will work. That's the more important one. Are we going to be able to inject in this aquifer? We don't know what the storage volume can be because we cannot have a closure and calculate it. We need to simulate how extensive with the plume, how much of that reservoir is it going to use? And then we don't know about the internal connectivity in the reservoir. And even if we characterize the reservoir through wells, mainly, you probably will not know whether fault, if the fault is here, whether that fault is sealing and making it a compartment or not. And I'll show you in examples, historical cases, what problems it can lead to. Now, why do we go to the pain of investigating these aquifers? Very simply because their capacity is so much larger than the depleted gas fields. So depleted gas fields are secure, but their volume comparatively worldwide are small compared to the capacity offered by saline aquifers. So this is the reason why we consider those as reservoirs, and they will need a lot more characterization effort to characterize the seal, the reservoir. Really, there's few logs, no core. So there's a lot of work to do to get the characterization of those. Now I'll move to the second point, which is the subsurface risk de-risking of site operation. Now this statement is always true. Choosing the right site is probably the most important step and the most important decision you need to take in the entire project. Why? Because we go from screening many sites, we try to get the best one, we select a few, we really look at which one is really the more convenient, then we go into a detailed design. By this time, you will end up, for your project, you will end up with investment decision, final investment decision. You'll have spent anything between 2 and 5 years. And you will commit now to construct the site, to license the site, to operate the site, and then to give the site back at the end of injection by plugging back the wells and restoring the surface condition. So you are embarking in a long project, and everything is based on what you do in the first 2 steps. Now, what are the risks in the subsurface? This is a summary. It's a few cartoons illustrating 5 main risks, and this is very common to any site, whether it's depleted gas field or a saline aquifer. So what you can have is a leakage through a plugged on abandoned wells. You know, if there are already wells that are there, this is our trap in the subsurface. This is where your CO2 would be, you know, schematically. And if you have any connection here, any conduit, like an abandoned well, and this abandoned well is leaking, then whatever you inject will actually come back to the surface, which you want to avoid. There could be leakage through fracturing. So if you inject and the injection pressure is too high, you may fracture the seal, you may leak through the seal. You may have leakage through faults. So if the seal is faulted, even if it's a depleted gas field and it's sealing, if you increase the pressure too much, you may reactivate the fault. Reactivation of the fault may be a conduit for escape. This escape may be a leakage. You can have a leakage outside if a plume is actually getting too big and that's moving outside too quickly. Then you can actually go out of the license area that you have, and you could have penalties for that. You could even have to stop your injection. And then you, of course, can have a leakage through injection or monitoring well. So these are different types of risks that you have, and we're going to explore those together. Now, how do we explore those risks how do we explore those risks through here? We have to explore those risks through building models and through analyzing data. So we analyze data the same way we do for oil and gas prospects and investigation exploration. We looked at well data, we look at seismic, we look at core data and hard data that we have, we look at all the drilling information that we have. But on top of that, we also look at geochemical data to look at reactions that could be introduced from introducing CO2. Now we construct different type of model. We make this a well type centric analysis to know whether this is safe and how the well will react. We looked at structural framework to understand the faults in the areas and the stresses in the area. We build a 3D static model, and we use this static model to derive not one model for dynamic flow like we do in the subsurface analysis for oil and gas production. We do multiple models. We do a geomechanical model and we do a dynamic model, and we couple those models to look at how the injection will change the stresses and will create possibilities or risks for mobilization of faults or fracturing and escape through the seal. And through this analysis, we answer a number of questions. We look at what will be the response possible, what will be a monitor in terms of 3D movement or changes in the stress field. We look at the well integrity. We look at how the faults will respond to this. We look at the subsidence. As we are injecting, we're going to change the pressure. We're going to create uplift in the subsurface. We're going to look at this uplift and what are the consequences of this uplift in terms of the long-term longevity of our site. And we're going to look at how we should develop our site, whether we should drill new wells or use existing wells. So all this is really driven by the modeling. Now, the workflow and technology behind, I will not go through it in detail, but the workflow and technology behind are really going through both model calibration and data analysis. Operation can use data and help us take immediate action. This is part of our operation monitoring planning. We have an assurance monitoring planning in which we'll verify that the conditions for injection are respected. We're not creating a major problem, and we look at the technology that can help us detect that. And then we also look at the models-based planning in which we have to integrate many measurements and different physics into models and make those models talk together so that we can predict what will be the consequence of our injection, design what type of survey we can implement to monitor that injection, and then design the execution in the field by designing instrumentation in the wells and designing surveys to be carried out during the life of that injection. Now let's look at the well surveillance and the risks and requirements and technology. If we go back to the different risks that we presented, this is going to focus on the two of them. Leakage through existing wells, they are there, we have to do something about it. And leakage through injection monitoring well, the new wells that we're going to construct. For this one, leakage through the injection and monitoring well, if these are new wells, then the first question or first answer is you have to do it right. You have to take every precaution so that the material that you use for these wells and the construction you make is resulting in a very safe and a long-term longevity of this asset. So you're going to use corrosion-resistant alloy, and you're going to use cement, which is CO2 resistant as basis for material. So let's look at that into more detail. So what is the problem of well integrity? We have here an example of well integrity for an injector well. There are several problems. There could be a different component that are leaking, and this induces a different degree of risk to the project. Yellow or orange is lighter risk, red is severe risk. So if we have got a tubing leak or packer leak, it's a risk. Every leak is a risk. But the advantage of a tubing or packer is that we can change them. So we could stop the injection, retrieve tubing and packer, and then upgrade them with fresh ones, and therefore avoid any other problem. The casing leak, we cannot do anything about it anymore. We would need to have a serious intervention onto it. If it's a casing, we can try to patch it. If it's a cement problem, it's very difficult to remediate. That may end up with abandoning or having to abandon the well altogether. Here are a few examples of what can happen. So this is a case of a leak through the tubing, a punch through the tubing. This is a case of a leak through the casing into the cement and formation. And this is the leak that is going through the cement out of the zone of injection into the formation and further out. Now, what instrument should we put in there? There's a balance between putting enough instrument to monitor the well and not creating areas or weaknesses in the well. But what we consider and what the industry is looking at the moment are these type of instrumentation. Remember that the instrumentation that we put in the well allows us to monitor the well without changing anything. So we monitor the well while the well is functioning and working. We do not have to stop it. We do not have to change anything. We do not have to introduce any objects into it, because anything we introduce into it could risk a mechanical problem like getting stuck, and therefore you could lose the well altogether, or it could actually create damage to the well and then require intervention or repair. So in this case, what we consider for is the use of new technology in the form of fiber optics. Fiber optics have been now proven to be used for not only thermal monitoring. In the thermal monitoring on the tubing is to monitor the phase and the temperature in the tubing, and to look at possible phase change, which we want to absolutely avoid in the tubing. And the fiber optics outside is to look for VSPs and being able to monitor the plume, monitor seismic without actually introducing any elements. Having a tubing for injectors does not allow us to put any VSP. We cannot run a VSP through it because we have no connection or contact with the casing and with the formation. So this one, once this is in place, unless we set an array of geophone behind the tubing and therefore are able to record some geophysical signal, where there's no way to install or to run a VSP through the tubing to record and to get a VSP. So this is kind of a summary, and this summary is for us to reduce the amount of intervention into it. So what kind of tool that we have with temperature, with the fiber optics, we can monitor, of course, the temperature and the noise. We can monitor the vibration. This allows us, if we look at the injection zone, which allows us to detect and see what is the injection profile. So we replace the PLTs. We have an information of where in the subsurface the injection is going. We have a monitoring of a strain and also monitoring of a temperature profile. We can look at warm back effect, and we can see where is the injection going, and then we can also look at an instantaneous temperature profile and then compare it through time and see that the injection is going in the right interval. So basically the fiber optics is very useful to verify that the well is functioning well and the well injection is going into the right place. It gives us also critical information about the reservoir, in particular the pressures that we have. Now, the fiber optics can also be used in seismic, and although the fiber is on the tubing, if a well is deviated, the tubing in contact with the casing, if the casing is properly cemented, you still could have a vibration measurement, and you could still look at VSP information from that one. So fiber optics definitely a very interesting and very important tool to reduce the risk. The only thing is you need to install it with the well. So when you build the well, you need to put the fiber optics and all the instrument in the well. I think we should emphasize a lot that there's a lot of opportunity for CO2 to deteriorate the cement for different reasons. This is proven in experiment, and there are CO2 resistant cement. these CO2 resistant cement should be used to avoid problems. Of course, we can have a cement bond log evaluation to look at the wells, but remediating a well where you have a free pipe, like in here, is a significant amount of work. So the best thing, the cement bond log evaluation is mainly used to qualify the well when we finish drilling the well, to make sure that the well is suitable, that it does not have spaces where they could be conduit for leakage. Corrosion is the main problem, but it's not too much of a problem on our injection well, even though CO2 is injected, because CO2 creates corrosion when it's combined with water. Now, when we want to inject CO2 in the subsurface to dispose of it, it is possible that we have a very pure CO2. And in this case, corrosion is very limited if it does not contain water. But it is also possible that the CO2 contains a lot of contaminant, whether it contains H2S, water, or other contaminant. This contaminant can generate corrosion. Now, to review corrosion, we have 3 different tools. One is a mechanical measurement. It's basically like a multi-finger caliper, and we're going to detect even very small holes in the borehole, and we get an image of that. That goes up to 80 arms on the caliper. Another one, which is more broad measurement, is going to be an electromagnetic measurement. The advantage of electromagnetic measurement is that it can detect well bore thickness, wall thickness for tubing, but it can also measure wall thickness for the casing. So you can actually make a measurement in the 2 sides, whereas if with a previous tool, with a caliper, you can only make the measurement inside the tubing you are in. You cannot have any information about corrosion on the casing. So this tool is quite useful, but of course it gives you an average value for the entire zone. It does not tell you whether it's a hole here or whether it's an overall thickness reduction over the entire area. So you have no geometrical sight on it. Finally, there's also, for areas of mechanical wear and tear, we can use some of the ultrasonic tools to detect holes in the tubings or in the casing. Now, the corrosion monitoring can also be helped once the corrosion goes to the point that you have a hole and you have a leakage, then you would go for detection of that leak. So the fiber optics can give you, through thermal elements, can give you very clear areas where you have leakage, and you can find those leakage. Another is from the vibration. You can actually detect also on the fiber optics, you can detect these elements, and you can also run a tool with a microphone to do that. So the fiber optics will be installed permanently and allows you, if it functions well, it allows you to make those detections without having to rely on a tool or to rely on the production logging tool. Now, this is a summary of all the well integrity elements and the different technology that we use. Fiber optics, the newest one, is actually quite useful and should be implemented or considered for at least in all the wells that we are going to drill, whether it's injection or monitoring. The production logging, cement bond, multi-caliper, electromagnetic, and ultrasonic, these are the tools that we would run inside the hole to be able to detect different elements, whether it's a leak, whether it's a hole, or whether it's a deterioration of a casing or a poor cement. These tools already exist, they are available, and they would be part of a monitoring of wells to make sure that the wells are functioning well. Now, the risk related to reservoir and the monitoring technologies are the other risks. So escape through fracturing, escape through fault reactivation, or lateral escape of the plume. So we look at the reservoir, we look at where the CO2 is, and making sure through models that we feel comfortable that the operations that we are given are going to keep it there. There is not going to escape through any different way. Now, these are an element of this. I wanted to just show you which is the combination of different tools. Again, if we have our subsurface, where we've got our seal and our reservoir, we measure the pressure in this. We take fluid samples in the aquifers above. We looked at seismic surveys to understand what is the extent of the plume. We may have observation wells. This is another injector well, but you may have an observation well where you're not going to inject, but you're going to log and you're going to maybe sample to confirm that the plume extent, what the plume extent is, and to note the arrival of CO2 in the subsurface. And then you're going to carry out a number of surface verification as well, which we're not going to go into at this stage, right? So going back to it, we discussed it. I'm not going to spend too much time for the monitoring wells. We've got the same thing where we're going to put a fiber optics behind the casing, and then we're going to put maybe some geophones. We're going to put these equipments. Here we've put the tubing so that we can come to the bottom and we could sample it. This is a condition that you may have. You may not want to sample it at all. You may actually decide to only log. You could detect the CO2 presence through the spectroscopy tools, and you could detect that variation of that difference. So there's different type of monitoring wells that you can set up, and depending on those, you can get the information to monitor the pressure and variation in the reservoirs, the arrival of the plume, the extent of the plume through seismic using these geophones for reception of a VSP. Now let's look into more detail into one aspect which is quite new. So the geophones that I was showing is this one. It is clamped on the tubing initially, and then it's unclamped and it's tied to the casing. It is permanently installed, and it will record all the events that we have here. Now we use these tools, but we also have another tools which could be very shallow. You don't need to drill a well. You have a station on surface. You have a monitoring tool which is buried. So we drill a very shallow, here 6 feet, it could be 10 feet, it could be 20 feet. But we drill a section in which we're going to put geophones inside the subsurface, and we're going to listen to the subsurface. So what are we listening to? This is not imaging like 3D or VSP. There's no source. We're listening to the rock failing and breaks that happen when we inject. When we inject to the subsurface, even if it's safe, if we below the frac pressure, there will be very weak zones that will reactivate. There will be some noise that you're going to record. And in particular, if you start to have reactivation of faults or reactivation of fractures or new fractures created in these weak zones, then you're going to be able to detect them. You're going to be able to detect them because they have a signal, they will make a noise. So if you're permanently recording, then you're going to be able to identify where is this recording, where this noise coming from, and what is the magnitude of that noise. And then from that, you can, if you start to see that there's a pattern where the noise are coming from the same place and the magnitude is increasing, that is telling you that your rock is starting to fail, and it's warning you that you should be more careful about injection. You might have to reduce injection. And we'll see that as well. Now, one of the new technology which is coming up, and I wanted to mention it here because it is still at the research level. There are some field tests that have been done, and there are some very interesting and very exciting results of these field tests, is to use the fiber optics not in the well, but to use the fiber optics on surface. And the idea here is that, as it's shown, that you have a fiber optic that is going round and round into different areas. And then basically, as you're measuring vibration along the length of that fiber optic, you actually have the equivalent of an array of geophones present on the entire surface. And this can be used to monitor the subsurface. It could be used to monitor monitor the noise and the passive seismic. If you continuously monitor, it could also be used to monitor when you bring a source and then you create a repeat batch 3D survey using this tool. You can monitor the area around the well, which is extremely useful at the very early stage of injection, when you want to know that there is no leakage around the well in this area. Now let's move to the main one that's been used for monitoring the subsurface and reducing risk is the 4D seismic, basically the repeat seismic. Here are a few examples. We're going to look at them in more detail in the final section of examples. But this is an example. There's a well-known example of Sleipner, which is an injection of CO2. And this is the extent of the CO2 bubble in 2008. The project has been stopped, I think, in 2019 or 2020. So it's stopped because the Sleipner field did not need to inject CO2, which had finished disposed of. The production, the CO2 associated with production stopped because production stopped. And then there's another interesting one which gets in, which is a very small project of a year of injection, where repeat 3D showed that we could monitor the extent of a bubble of CO2, and even if it changes through time, even way after injection through this solution. So we see that the bubble is increasing, is further increasing even after injection has stopped, because the CO2 reorganizes itself in the reservoir, therefore comes to the top of the reservoir and extends laterally, and then it goes back again because it starts to dissolve. Now, what is possible, and the reason why this is possible is because between 2000 and 2010, there was a significant improvement in the accuracy of repeatability of the 3Ds, especially for marine 3D. For onshore 3D, of course, the repeatability is possible. We need to confirm that. To do that, we have better tools and acquisition tools for this that has increased the repeatability. It's just the cost, which is much more expensive onshore, which limits the amount of experiments that we have done. Now, what do we do with this information of 4D? Of course, we can look at the extent of the plume, but in itself is not giving you a full understanding. You need to know how much CO2 is actually extending and where is it extending and what is the pressure and how is it going to move and what are going to be the impact of this. So this is a case, what I'm going to take, it is not an injection, it is actually a depletion. This is a field that has gone under depletion, and because it has gone under depletion, then the stress changes. But it's the same thing. If you inject into an aquifer or into a gas field, you will increase the pressure, the stress will change. You want to look at the stress changes and their impact. So the principles are the same. We already have a technology. We can model the subsurface in terms of movement of fluids. We can model the subsurface in terms of geomechanics. And therefore we can combine the two, which is the coupled modeling, to know what are the geomechanical implications of a change of pressure. And here it is. In our model, this is the reservoir model with a pressure prediction that is proposed, and that's based calibrated on the pressure measurement at the well. So we know that pressure measurement at the well is correct, and these are the different pressures in pressure scale inside the reservoir. Now the stress changes because the pressure change that we have here, because of that pressure change, we have stress changes, and we are now able to calculate those stress changes related to those pressure changes. And the calculation of pressure changes and pressure changes allow us to compare with a 4D seismic. We're not comparing here pressure in terms of amplitude. We're going to compare pressure in terms of delta T. So we look at very small variations between 4Ds, between 3D surveys, very small variation on how the loops are changing. Here in the case of the base case of acquired 1996 and the monitoring surveys acquired 20 years later. And we look at very small time shift. You see, the scale of time shift is 1.5 milliseconds. So it's at the level or less than the level of a sampling. Now we looked at those time shifts, and the information that we get is actually extremely enlightening. This is the comparison between several surveys, between 96 and 2005, between 2005, 2012, and between 2012 and 2016. So the time shift that we measure between those successive surveys can be correlated with the amount of depletion that we have in this. So the greater the depletion, the greater the time shift observed. In this case, the reservoir is a high permeability. The depletion is very severe. There's a very strong time shift. In this case, the time shift has been strongly reduced because the reservoir has regained pressure towards the end of production. And now that the reservoir has no more depletion, then it is restored to something similar to what you have. We don't see a change anymore. So these elements put together between the 4D seismic, not some on the amplitude, but also time shift, help us tremendously. The integrated studies is another example. It's a much larger field in which there was a pressure change between over a period of 10 years. This was modeled in terms of stress change, and the stress change was modeled against subsidence. So by this pressure change, there would be compaction in the reservoir. The compaction would actually translate in a deformation of the surface with a subsidence. This was compared with the actual subsidence measured from that field. And the 80 bar change in the pressure caused a 2.5 meter subsidence. The fact that these two are actually comparable tells us that we are able to look at the stress changes from the reservoir point of view and the geomechanical models. We are able to compute the stress changes related to, in this case, production, but again, will be the same for injection. We can compute those and we can transform them into an expected subsidence. And then we can compare that subsidence with the subsidence observed for that field. So that allows us to track indirectly the extent of a plume. Now with this, I would like to conclude very soon with a few example cases. So there are quite a few cases of injection through time. The earliest one and the most documented one is probably Sleipner, starting in 1996. But there are 5 of them that I'm going to go through to mention some characteristics, not in detail of all of them, but some characteristics. So Sleipner is an injection to get rid of CO2 that is produced from the field and from the gas from other fields around Sleipner, going to the platform. And Sleipner had to, or the team had to get rid of that gas because they needed to remove the CO2 before shipping the gas to shore, to condition that gas to proper specification. So the CO2 was initially released in the atmosphere, and the government says, no, you cannot do that. That's global warming. You have to dispose of it. If you do it, then you'll be fined. So to avoid a fine, then the company decide to, Statoil at the time, which is Equinor now, decide to dispose of it underneath. They found a very high permeable sand, sealed, and then they drilled a very long reach well, and they drilled that long reach well to make sure that the bubble of CO2 that you have here would never go back in the time that they inject and they produce the field. They will never go back to this and start corrosion issue here. So they drilled this extended well, which is this one that you have here, They completed it in a way that it would be stable, and then they did the injection, and they reached about 1 million ton per annum of injection on average for the 20-year period. Now this is the platform, and this is the injection point at the end of this long extended reach well, and the injection point is around here, right? Now you can see that 1994 was before injection. This is the 3D before and what it was. This is a 3D acquired. There are several 3Ds, intermediate 3Ds acquired, but this one is acquired in 2001. The injection is here. You see that the CO2 has started to move up and down or rather up and up and up inside the reservoir, and it stays under the seal. So we have confirmed that there is no escape through the seal, and CO2 is occupying some space inside the reservoir. As you continue in 2006 and 2010, then the plume continues to move, and now it's gaining momentum. It starts to spread further out, and it reduces in the low part, but the injection is still continuous. Now, this is the lateral extent of that, and you can see that over time, the plume is moving into a never larger area. It never reached the platform, so the objective of injecting this CO2, storing it underground, making sure it would not reach the platform, was actually reached, and therefore it's a successful project. Now, this one is not so successful project. This is the same problem. CO2 is produced as part of a gas because there's a fraction of gas of CO2 in the gas that we produce. So we need to condition it before we ship it. This is in the south of Algeria, very far from anywhere, any market. So you need to actually ship the gas over a pipeline that you have here, and you need to condition it before you can do that. So to do that, what they did, they drilled specific wells to inject into the aquifer. Because we're depleting here, there's a hope that the aquifer would not be pressurized. You would be able to inject into the aquifer. So this was actually started in 2009. There was a couple of issues with a leaky well that they needed to fix, and then which they did, and then they continued. But there was a problem. The permeability of this reservoir is actually quite low. So when they were injecting at the beginning, they didn't see any microseismic activity. If you remember what I mentioned, the microseismic activity will detect fractures and fault reactivation as they happen in the reservoir because of the noise they create. So this is the level, in black is the level of microseismic activity. In red is the injection level. In the dashed line that you have here is the objective of the target to be commercial, this to be of attractive interest, basically to be able to dispose of all the CO2, you would need to reach a steady plateau injection at that level. This is the attempt. So it started into production, went to production, or rather into injection of CO2 in this aquifer, managed to pass the target, but when they did, they started to have some hints that there was some crack happening. They tried to investigate and find out what was the problem. They tried again after a while, and then the problem came back. Again, that was the time that they were looking at whether there was any fracture in this area. Then they started again in this point, and at this stage, they were able to reach the plateau for a short period of time. Then significant amount of induced seismicity was recorded. They tried to cancel that by reducing the injection, but they could not bring it back to zero. So coming to a point that they had to stop. They had the last attempt to do it, and when they restored it and injected, then it came to a very high level. At that point, they realized that they were not able, despite different attempts, to do that, and they would have no chance of reaching their target of injection. Therefore, this project altogether was cancelled. Why? Because compressing the gas, disposing of it is actually quite expensive. If you do not get the benefit from carbon credits, then you don't get anything, right? So you may as well vent it. So in the case of Snøhvit, project, this is a project also by Equinor in the very far northern part of the North Sea. And it's also the same problem. A CO2 is produced because there's CO2 inside the gas that we produce. It's very far offshore, very far from the market. And again, the same thing. You need to condition the gas before you do that. So you need to dispose of it. And one of the solutions is to reinject it into a different zone. In this case, they didn't reinject into the aquifer of the same reservoir, then reject it into another aquifer, which has got a very small accumulation, but it is not in the development. The problem on this one is that the structure that they are looking at is actually conditioned by a lot of faults. It's a host and graben environment, and these faults are actually sealing. And the faults that are sealing, they present obstacle to the diffusion of the pressure, meaning that when you inject, the pressure will only diffuse across, away from but it cannot diffuse in this area, cannot diffuse in that zone. And this is compounded by the fact there's a large variation in permeability. So if your channels or your better permeability are oriented in this direction, then the diffusion of the pressure away from it along the structure is not possible. Now, what happened is the following. They completed the well, they started the injection, and they recorded the pressure. And they realized that the pressure was going up. They tried to analyze that through different ways, and they were not able to solve it, meaning that the pressure would always go up. There's nothing you can do. You cannot recreate the subsurface, change the faults, make them transmissible or anything. Once this is set, this is what you have to live with. And this is why at the beginning I mentioned the decision of choosing the right site is the most important decision of the entire project. Now, of course, this is a site very far from anywhere. You don't want to ship the CO2 somewhere to inject it. So the cheapest option is to inject it where you produce it. And this is what you should look into. Their first attempt was a failure because they could not actually keep the pressure down. They drilled, therefore, a second well in a different formation that got much higher permeability, and they were able to inject into it. So they first actually not drilled, but they reperforated into a different layer, and they were able to inject in that layer. And then since it was not sufficient, then they drilled a second well to reach a separate fault block and store in that fault block. And they did 4D monitoring to verify the changes. And this is the traditional 4D monitoring, highlighting these areas where not much is happening, which is in white and grayish, and the areas where you have got softening and hardening from water coming, softening from CO2 or gas replacing water. Now, another project that is important, and again, the same thing, producing gas with high fraction of CO2 coming to the shore where the plant is processing it. So this is deep water. There's no platform with offshore treatment. These are subsea wells. The tie back to the island here offers a problem. This is an island which is a natural preserve area. So there's very limited information, things that you can do. You need to have permission for anything you would do, any well you would drill, any operation that you carry out. So we needed to plan for this, but this is the place where the CO2 comes together with the gas, where the CO2 is separated, and you need to do something with this. So the idea was, again, let's try to inject it where we produce it. And this was the plan, just to be able to inject in the subsurface where it's actually close to where it is separated, and they enter the problem. So I'll cut it short. They made a detailed study. They looked at what they needed. They realized they need to have many injectors and several extractors. But in the initial plan, they decided to have limited number of injectors and no or limited available numbers of extractors. And one of the reasons is that if you extract the water, then you still need to dispose of it. You cannot dump it because this is saline water. This is a protected area. You would need to actually re-inject it into yet another aquifer. So you inject into a deep aquifer, the pressure goes up, you produce some water to reduce, then you re-inject that water into another aquifer where you will dispose of that water that you cannot dump out. So this injectivity risk was significant. And in the end, this caused major delay in the project. Project was initially to be done in 4 years. After 10 years, it barely reached the objective that it had of 4 million tons per annum of injection. So 6 years of production where there was no injection. Now, you cannot take that and go to the client and say, I'm going to take care of your CO2 in 5 years or 10 years from now, or 5 years when my project is ready, sign on this price. You cannot go back to him and say, by the way, the injectivity is not so good. We need going to have to delay that for another 5 or 6 years. There will be penalty clauses, so serious consequences for your decisions. Now, in the Illinois Basin, it's another example. The amount to inject is very small. Again, the same thing. This is now an industrial process producing CO2, and we want to dispose of it in the same place where we produce it. This one is actually a success, not because the formation is suitable, but because the formation is very, very large. So there's a very, very large reservoir. There's a very, very good topsoil. And the injection volume that we have are very small compared to the size of the reservoir. So over a large period of time that you have here, we talk about 10 years from the start of injection to this, the plume that we are considering are only in the order of a kilometer. Now, this is still a problem in the US because the US is very strict about license, respecting the license that you should not exceed the license area. And therefore, you could have strong penalties by the owner of the land or in the other areas outside of your license areas. Now I'll come to conclusions on risk and risk management to take. First is choose the right site. That's the most important thing you need to do. That's not even the risk management, but it is really risk avoidance. So from the beginning, if you want to improve risk management from the start, you must choose the right site. You must characterize the site to reduce all the uncertainties. And if you want to inject into an aquifer, you've got lots of uncertainties remaining. So for aquifers, plan for a big exploration program. It doesn't mean a lot of wells, but it means a lot of measurements in specific wells, maybe 1 or 2 wells. But you take core, you take good logging, you take sidewall scores, you take a lot of measurements, and you're going to do a lot of lab measurements. You plan to instrument the site, meaning that when you construct the wells, you need to set them up with the right instrument so that you don't need to bring tools or to interrupt the production or the injection, and decrease the risk of operation failures, like having a fish or having a mechanical obstruction in the well due to the consequence of the operation. You need to monitor the well and the reservoir and the overburden. You need to monitor all 3 of them. The wells, to know that the wells are in good condition, can continue to inject. The reservoir, to know where the CO2 is going. And the overburden, because you want to detect any early place where the CO2 might have reached. So for example, if you inject CO2 in a depleted gas reservoir, the seismic might not change that much. But the seismic will detect escape of that CO2 in the overburden when the spade starts. And therefore, it will help you to point or pin down areas where the subsurface is leaking. You will not be able to fix fault or fix, if it's a well, you can fix it. If it's a fault or if it's fractures of a seal, you probably cannot fix it, but you can see what will be the consequence. In general, we consider this reservoir with multiple reservoir seal pairs. So we've got the main reservoir and seal, and we've got in the overburden reservoir seal pairs. The monitoring of the reservoir overburden will also tell you what should be done if a leak is detected to prevent that leak from reaching the surface. And there are several solutions that you could consider. But for this, you need to have a proper model to know what solution would work and which one wouldn't work. And then you need to prepare contingency plan for risk scenarios. It's not when the risk is happening or when now it's materializing in an event that you need to have a contingency plan. So there's a lot of preparation work in the risk management aspect, just like we do for QHSE management. The other conclusion is that data acquisition is key from reservoir and seal. You need to do that from the beginning. Modeling is absolutely key. You need to do static, dynamic, geomechanic modeling with coupling. You need to include geochemical aspect of the stress, the geochemical stress or chemical stress on the formation, on the reservoir, on the seals. You need to look at the site performance, and you need to, that site performance depends both, you see, on capacity and injectivity, how much you can store. You need large enough volume, how much and how easily you can store, so you reduce the number of wells and the effort to compress the CO2. But you also need to choose a good containment that the performance of this site will allow you to inject and meet your targets, not like in failing. If you remember, in Salah project is a failure of containment. It's not a failure of capacity, there was enough space. It's not the failure of injectivity. We could have pushed the CO2 and they managed to inject the target rate that they have. It's a failure of containment. Then during execution, you need to have continuous monitoring and model update. Why? Because not only it is required to optimize your site, but it is, for example, if you realize the site can take even more, then you could get some prospective client. Without changing much, without much investment, you could get a lot of additional revenue. But more importantly, you need to make sure that you satisfy to regulation and you're going to be able to continuously inject. You will not have your license withdrawn. You will not have public opinion building against you and trying to cancel your project. And you will not have major risk of delaying the project and therefore having penalties or fees with the contract with the emitter that you have signed that is now exposed to penalty because you cannot take the CO2 that you committed to take to dispose of. So this is fundamental. You will have to not only do a very good characterization at the beginning, but the continuous monitoring. And with this is the end of my presentation, and I would be opening for questions.
Thank you, Mr. Francois, for your informative presentation, and thank you all for your attention. Unfortunately, since the time is over, we won't be able to have any question, but if there is any question, they can send it for EAGE member, and they will share it with Mr. Francois. Thank you again for your time, Mr. Francois, and thank you for attending.
Thank you very much.
Thank you.